morning, good afternoon, good evening, depending on where you are watching me from. My name is Dr. William Atokolo, PhD, Applied Mathematics. Today, I want to discuss on what mathematics can do. We are tired of finding X and Y. Mathematics has gone beyond the level of finding X and Y. Now, what can mathematics do? That is why I want to teach us, that is what I want to teach us today, mathematical modeling. And we want to consider mathematical model for the spread of tuberculosis. That is, we can use mathematics to study how disease spread in a community and how to also control it. That is one of what mathematics can do. And also call it mathematical epidemiology, that is biomathematics. Now, we want to formulate a model for the spread of tuberculosis. Tuberculosis is an airborne disease. That is, it is transmitted in the air, that is through the air. Now, we divide the population into 4 compartments, that is 4 classes. So the first class, let's assume that we have what to call the susceptible population. S is susceptible. Then we have what to call the exposed population. We also have what to call the infected population. And lastly, we have what to call the recovered. Look at it again. I say X is susceptible, E the exposed, I is the infected population, R is the recovered population. What is the meaning of susceptible population? That is those that have no disease. Let's assume that you and I, we are susceptible to tuberculosis for now because we don't have the disease, but we may likely get it if care is not taken. The exposed are those that are infected, but they are not yet infectious. They cannot infect anybody because they are not yet infected, but they are infected, but not yet infectious. But this I is for infected. They are infected and they can infect someone, that is infected and also infectious. Now, the R is the recovered. Those that recovered from the disease, and as such, they are removed from the population. Now, let us assume that the rate at which people come into this population, that is the susceptible population, let's assume that the rate at which people come into the population is lambda, which is this sign, lambda. That is, it will be by birth or through immigration. So the rate at which people come into the population is taken to be what? Lambda. Now, this is the exposed population that I explained before, and this is the infected population, why this is recovered. Look at it now. For someone to be infected with tuberculosis, that person will have to contact or come in contact with the infected. The infected is what? I. So let's assume that the contact rate is beta. These people here, they don't have tuberculosis. But for them to be infected with tuberculosis, they will have to come in contact with an infected tuberculosis patient. Now, let's assume that beta is the contact rate. Beta here is the contact rate. So Xi, look at it now. This X, this person has no disease, but the I has disease. So there must be a contact between the susceptible and the infected before this person is infected. So beta now is taken as what? The contact rate between the susceptible and the infected individuals. Now, the exposed. So, and before you know, they'll be exposed. Now, we assume that the exposed are fully infected at the rate of, let me use alpha. They are infected at the rate of what? Alpha. That is, after some times, when the signs start showing, those that are exposed to tuberculosis will be fully infectious and at the rate of what? Alpha. And now, they can recover at the rate of what? At the rate of gamma. So let's add I here. Let's multiply by I because it's leaving this I population. Now we also multiply by E here because it's leaving the E population. Look at it again. This is alpha. That is the rate at which they expose becomes fully infectious. And now at the rate of what? Lambda. That is why we are multiplying by what? E. Then because this E is exposed. Now this is gamma I. Gamma is the rate at which the infected, those that are infected and are infectious, the rate at which they recover. And that is why we multiply by I. Now we assume that there is natural death. All the classes, everybody must die naturally. So let's assume that the susceptible, those that have no disease, they can die naturally. So let's use maybe mu. We call it mu. This is mu in mathematics. Mu S. The exposed again can die naturally. Mu E. Then the infected can also die naturally. Mu I. Then the recovered can also die what? Naturally. Mu R. But look at it now. What is natural death? When you are sick, even if you are not sick of tuberculosis, even if you are not infected with tuberculosis, you can have accident and die, God forbid. So we call it natural death in this case. But it's not a natural death from God. But in this case, it's natural death because it's not tuberculosis that kills such a person. So we call it natural death. But when tuberculosis kills someone, we call it disease-induced death. And as such, that one will come here. Look at it now. We have an arrow here. So let me use theta. Theta I. That is, theta is the rate at which those infected with tuberculosis die of the tuberculosis. That is why when you share, we have two death rates here. One is mu, the natural death rate, and this one is what? Disease-induced death rate for the infected and infectious class. Now, we also assume that, when you recover of tuberculosis together by treatment, you can still be susceptible again. That is, you can lose immunity and then return back to be susceptible. The fact that you recover today does not mean you will not be sick of tuberculosis again. When you are not very careful, you can still be what? Susceptible. That is why there must be an arrow or a connection between this. That is, this population, those people here can still move to that, can still progress to this. Let's use maybe phi what? R. So that is phi is the rate at which they recover, become susceptible again. Now, let's formulate the model. We formulate the model. This is what we call the model flow. This is what we call the model flow diagram. All right? For tuberculosis. But this is a simple model. We call it SEIR simple model for what? Tuberculosis. So now we write the equation. Now let's write out the model equations. The first one is susceptible here. So we say change in susceptible population, that is the S, the T. Now, how do we write? Look at it. Any arrow, anyone that is coming, look at this one. This lambda is going inside, that is coming into the population. So we use what? Lambda. It's going, so it's positive. But when you check, anyone that is going, look at it now. Beta Si is leaving susceptible, so it will be minus beta Xi. All right? Then which one is leaving again? Mu S is leaving. This one is leaving. So, but look at it. Phi R is coming in. So since it's coming in, we can say plus phi R because it's coming into the X population. Now, but mu S is leaving, so it will be what? Minus. So we have written out the population dynamics for what? The susceptible compartment. Now let's move to the exposed class. We have the E, the T. The E, the T, look at it very well. Beta Si is entering, so we write it first. Look at it. And then this is leaving, that is alpha E is leaving, and then mu E is leaving. You see now, we have also written out the equation for the exposed population. Now, let's move to the infected class. That is the I, the T is equal to what? Alpha E is entering. Look at, because it's entering this class, then this is leaving, and this is leaving. So you have minus gamma I minus theta I, then minus mu I. Now we are left with the recovered population. Then it will be what? The R, the T is equal to, so gamma I is entering, then this is leaving, minus phi R, then this is leaving, this is natural death rate, so minus mu R. As you can see, we have successively formulated a model for the spread of tuberculosis in a population. So this is now the model equation. Thank you very much. Please join me again tomorrow for another tutorial on the same topic. Thank you. Bye-bye.